pre-calc honor students. Here we are with sum and difference formulas for sine and cosine. And they're kind of tricky because a lot of students mistakenly think, oh, this is just cosine alpha minus cosine beta, and they distribute the cosine over subtraction like it's some kind of multiplication. No! That is junk. Do not do that, please. You do not distribute trig functions over addition or subtraction. But the only thing you distribute over addition and subtraction is multiplication. That's it. So how can we come up with a formula for this? Well, we can call this angle alpha in here, and that's from here to here. And let's put it on the unit circle. So on the unit circle, this is cosine beta comma sine beta. Because I'm on the unit circle. This is a unit circle. Now, we have two ways to figure out what the distance is between these two. Because I set them up like this, this angle in between is alpha minus beta. And so I can first use our recently proven law of cosines to come up with what this length is here. And let's just call this AB. You can get AB, distance AB, by saying that distance squared equals 1 squared, because this is a unit circle, each of these is 1, plus, plus 1 squared minus 2 times 1 times the cosine of alpha minus beta. That's the law of cosines. So AB squared equals 1 minus 2 minus 2 cosine alpha minus beta. Okay, now we can also get AB from the distance formula. Because I have the coordinates of these 2 points, we can say AB equals the square root of the difference in the x's, that's cosine alpha minus cosine beta squared, plus the difference in the y's, sine alpha minus sine beta squared. And then square both sides, so AB squared equals cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. So we can set these two expressions equal. These two expressions must be equal because they're both equal to AB squared. So let's do that with miracle cut and paste. Show it up over here and set that equal to equals this whole expression here. Okay, maybe make that a little smaller. Now it fits in there. Okay, now we got a little work to do here as we start expanding this stuff out. So, and let's clean this up a little bit. This is 2 minus 2 cosine alpha minus beta equals all that squared and all that squared. Need another page. So 2 minus 2 cosine alpha minus beta equals cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta plus, now I expand out this part, sine squared alpha minus 2 sine alpha cosine alpha plus sine squared beta. So we get 2 minus 2 cosine alpha minus beta equals cosine squared plus sine squared, these two add up to 1. Cosine squared beta plus sine squared beta, those add up to 1. Minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. So the 1 to 1 is 2. Those cancel from both sides. And can divide through by a negative 2. And so you get the cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Okay? Now we can transformationate this into, we can think of cosine of alpha plus beta then as cosine of alpha minus a minus beta, and apply our new formula then, cosine alpha cosine negative beta plus sine alpha sine negative beta. Now cosine is even, so that's why cosine negative beta is cosine beta, and sine is odd, so sine of negative beta is negative sine beta, so that's why it becomes a subtraction. So cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Sine of alpha minus beta is a little trickier, but we can view it in terms of sine is equal to the cosine of 90 degrees minus alpha minus beta using the cofunction trick. And then we change this into the cosine of 90 degrees minus alpha plus beta. And so using the cosine sum formula we just proved, it'll be cosine of 90 degrees minus alpha cosine beta minus sine of 90 degrees minus alpha sine beta. And using the cofunction idea again, cosine 90 minus alpha is sine. Sine alpha cosine beta minus cosine alpha sine beta. So with the sine subtractions, you end up having a subtraction retained, but then you shuffle up the sine and cosines. With the cosines, you get cosine, cosine, sine, sine, but then the sign switch here, notice the alpha plus beta and cosine is minus here. And so you can do the same thing to prove that, and you end up with sine alpha cosine beta plus cosine alpha sine beta. There's your trig addition formulas for sine and cosine. Now let's find the exact value of the sine of 15. 15 degrees is not one of our special angles yet. But we can write 15 as 45 minus 30, which are two of our special angles. So now I can use the sine expansion. Sine 45 cosine 30 minus the cosine of 45 sine of 30. And these values you should have memorized, and this should come just tripping off your tongue here. Square root of 2 over 2, cosine 30 is square root of 3 over 2, cosine 45 is square root of 2 over 2, sine 30 is a half. So that's square root of 6 minus square root of 2 over 4. That's the exact answer. Now I put it to you that we can add the 15-degree angles as some of our special angles, because you can, if you want to, look at this thing out in the Flange Wiki space, handy forms, under the page handy forms. I've got ways you can practice filling out all your special angles from before, but now the special angles every 15 degrees. And the chart is daunting when you first look at it. You go, oh, no way I can know all that. Well, just hold the bus, kids. Look at this. Look at just the first quadrant here. Actually, it went up to 180 about. And notice what's happening with the pi over 12s. We just did the sine of 15 degrees, square root of 6 minus square root of 2 over 4. The cosine ends up being square root of 6 plus square root of 2 over 4. Both these are positive values. The cosine value is bigger because you're at this shallow angle right now of only pi over 12, where the x-coordinate is much bigger than the y-coordinate. Notice as we go over to 75 degrees, the two have flip-flopped. They're both positive, but now sine is the big one and cosine is the other. At 105 degrees, sine stays big. Now cosine has gone negative, square root of 2 minus 6. So your k pi over 12 answers for both sine and cosine yield plus or minus square root of 2 plus or minus square root of 6 all over 4. And you can just figure out from the picture if this thing is positive or negative, and also if it's really positive or just slightly positive. Okay? So it's really not that daunting once you get this idea down, that the 15 degrees, the over 12 answers have sine and cosine answers like that. Now you should also be aware of going backwards. That is, find the exact value of this. Well, rather than trying to figure out 50 as a sum of things, we can view this as the expansion of the cosine of 50 degrees plus 10 degrees. Because it'd be cosine 50, cosine 10, minus sine 50, sine 10. So that's the cosine of 60, which you should know from looking at your unit circle, cosine 60. That's the square root of 3 over 2. No, cosine. Cosine is the x-coordinate. That's 1/2. Okay, all without a calculator. This next test, no calculators allowed in Chapter 10. Similar thing going on here. This is the sine of a sum of angles expanded out, and it ends up being the sine of 5 pi over 12 plus pi over 12. So that's the sine of 6 pi over 12, or the sine of pi over 2, which, you look at your unit circle, you go straight up, the y-coordinate is 1. 1. Okay. All right. Now let's do a slightly more complicated problem. Suppose you know the sine of alpha is 4/5 and the sine of beta is 5/13, where alpha is between 0 and pi over 2 in the first quadrant. Beta is between pi over 2 in the second quadrant. Find the cosine of alpha plus beta. Well, our outline for this is to do the expansion. That is cosine alpha, cosine beta, minus sine alpha, sine beta. And we go, oh, look at that. We've got the sine of alpha. That's 4/5. A lot of kids mistakenly think that I am telling them alpha here, and I see this too often. I see sine of 4/5. No. The sine of alpha equals 4/5. So I replace all of sine alpha with 4/5, and all of sine beta with 5/13. Of course, we don't have these yet. Oopsie, how did that happen, people? Well, we can find them. Because the sine of alpha is 4/5. So let's make a diagram here. Now, I'm going to expand on this idea. Sine of alpha is 4/5, and it's in the first quadrant. So that means the hypotenuse is 5 and the height is 4. So there's alpha. Sine of alpha equals 4/5. So then we can use those two ideas to come up with 3, the other part of that Pythagorean triple. So the cosine of alpha is 3/5, and we can fill that in over here. 3/5. Now our other diagram is the fact that we've got sine beta equals 5/13. But it says beta is in the second quadrant. So I'm going to make only a height of 5 this time and hypotenuse of 13. And I think you remember that Pythagorean triple. 5, 12, 13. But it's going to be a negative 12. So we get the cosine of beta is a negative 12/13. And that goes in over here. Now we can finish up our problem from before. So we get negative 36 65ths minus 20 65ths, and you end up with negative 56 65ths for your answer. Oddly enough, that ends up being another Pythagorean triple. It's the famous, well, let's find out on the calculator. It's the famous 33, 56, 65 Pythagorean triple. Maybe that's not so famous to you. And admittedly, I have not seen it that much. But one thing you'll find that if you start with a couple Pythagorean triples, the combined angle, whether it's a subtraction or different, ends up being a Pythagorean triple again. Now, let's see what we got here for example 4. Show that sine of 3 pi over 2 minus x equals negative cosine of x. So we can just expand this out. And we get the sine of 3 pi over 2 cosine x minus cosine 3 pi over 2 sine x. Is that equal to negative cosine x? Well, sine of 3 pi over 2, whenever we go on the unit circle, 3 pi over 2, the y-coordinate, we're down, it's negative 1. Negative 1 times cosine x minus cosine of 3 pi over 2, the x-coordinate is 0. So that term falls out. And we just end up with negative cosine x equals negative cosine x. There's your proof. Okay, I believe that's it. Flange out.